This is slide number 57 and I am your presenter Asloob Mudassar. Coherent imaging system. You see that we started earlier in the previous slide about the polychromatic light sources. So you see here we are going to discuss the coherent imaging system for such a system, for such a narrow band polychromatic light source. So let's assume that zeta 1 and eta 1, that is at the origin of the coordinate system, where zeta 1 is equal to 0, eta 1 is equal to 0, as a phase reference point, which means that the phase of all object points other than the origin, that is zeta 1 is not equal to 0, eta 1 is not equal to 0, will be expressed in terms of the reference phase value at the origin of the zeta eta plane. The phase at the origin will be subtracted from the phase value at all the points of the object plane. That is, we are referencing the phase of all the object points with respect to the phase at the origin. Let's designate the phasor at the origin by UG, at UG as a function of 0, 0, time. That is, UG is only time dependent because the coordinates there at the origin are 0. So the phasor at the other point, that is at the points zeta 1 and eta 2, is equal to UG at zeta and eta and time is equal to the spatial part of the phasor, which is UG of zeta 1 and eta 2, and the time dependent part of the phasor, which is UG of 0, 0, t. So here you see that we are referencing we are writing down the phasor at the point zeta 1 and eta 1, and you see that here we are including the phasor, we are including the time dependent part from the origin, so that we can reference the phase at this point at the zeta 1 and eta point with respect to the origin. The spatial part of the phasor at the point zeta 1 and eta 2, that is UG of zeta 1 and eta 1, is multiplied by the time dependent part of the phasor at the origin, that is UG of 0, 0, t, to obtain the complex phasor. So you see that here we have described that we can write down the complex phasor at the object plane using the spatial part of the phasor at that point multiplied by the phase reference with respect to the origin, that is the time or the temporal part of the phasor taken from the origin. The phases at all object points thus change with the change of a phase at the origin. Such a type of a phase relationship is due to coherent object field. So you see that we can only reference the phases at the other points with respect to the origin only when we are discussing the coherent system, that is our field at the object plane, that is at the zeta and eta plane, is coherent. So under such a condition we can write the phasor as described above. It is necessary for the spatial parts of the object phasors to retain correct information about the intensity at the object plane. For this we need to introduce normalization constant. We can thus express the phasors at the object points in the following way. So you see that now we are going to introduce some normalization constants so that we can obtain correct information about the intensity at the object plane. For that one we are going to write equation number 14 and 15. So you see that in the equation number 14, let's describe that we have on the left hand side UG as a function of zeta 1, eta 1 and time is equal to the spatial part of the phasor at that point, that is UG of zeta 1 and eta 1, multiplied by the time dependent part of the phasor taken from the reference, that is UG of 0, 0, t, and divided by some normalization constant, which is the square root of the averaging of the time averaging of the absolute value of the phase at the origin. And similarly, we have written down equation number 15 for another point, which is zeta 2 and eta 2. That is on the left hand side, the spatial part, the ug is equal to zeta 2 and eta 2 at the also with respect to time is equal to the spatial part of the phasor, that is ug of zeta 2 comma eta 2 multiplied by again the time dependent part of the phasor, that is ug of 0 0 comma t, and also divided by with the normalization constant, which is the square root of the time averaging of the absolute value of the phase at the origin. So equation number 14 and equation number 14 have been written in the normalized form. Especially the time averaging part has been normalized, because due to the coherent field, the spatial part at point zeta 1 and eta 1, and the spatial part of ug at point zeta 2 and eta 2, and equation number 15 as in equation number 15 will not change because they are time independent quantities. So the time dependent quantities have to be normalized so that we can obtain correct information about the intensity. When we write down the intensity using the left hand quantities ug as a function of zeta 1 eta 1 and time, and ug as a function of zeta 2 eta 2 and time. Now you know we have written equation number in equation number 13 the mutual intensity between the 2 points also as a function of time. So let me read that one, that J subscripted to G as a function of zeta 1 and eta 2 and colon zeta 2 and eta 2, that is the mutual intensity between these 2 points zeta 1 and eta 1 and zeta 2 and eta 2 is equal to the time averaging of the phasors at point zeta 1 eta 1 at a function of time multiplied by the complex conjugate of the phasor at the point zeta 2 and eta 2, and also with respect to time. So you see that we have encountered this expression once previously, and now we are writing this again, and you know that this is very well valid for a narrow band polychromatic light source. Now you see that now we have obtained the expressions for the coherent system, because we have referenced the phases of the other point with respect to the phases at the origin, and we have written for the 2 points in equation number 14 and equation number 15 respectively. So we are going to plug in these values in this expression of the mutual intensity, that is Jg, obtained from the polychromatic light source. So putting these values over here, and you know that we can separate out the spatial parts. As in the second case, we can write on the right hand side of the equality, that is ug, that is the spatial part of ug at coordinates zeta 1 and eta 2 multiplied by the complex conjugate of the spatial part of the phasor at the point zeta 2 and eta 2. And you know that the time averaging brackets is on the 2 quantities which are contained within these averaging brackets, and the time averaging is with respect to time. So the time averaging brackets contain ug of zeta ug as a function of 0 0 and time divided by the normalization constant, and similarly complex conjugate of the phasor at the point 0 0 and t, and again divided by the normalization constant. So combining these 2 quantities, these averaging will be applicable only to the quantities at the numerator, because the denominator are already averaged out with these averaging brackets. So we have taken the average of the numerator over here. Now you see that this numerator is the same as the product of the 2 terms on the in the denominator. So the numerator and the denominator will be exactly cancelled out, and we can write the equation number 16, that the mutual intensity between the 2 points zeta 1 and eta 2, and between the 2 points zeta 1 eta 1 and zeta 2 and eta 2 is equal to the field at the point zeta 1 and eta 1 multiplied by the complex conjugate of the field at the point zeta 2 and eta 2 as in equation number 16. And you will notice that in equation number 16 there is no time dependence, because the time dependence has been cancelled out during the averaging process and during the normalization process we have done. So let's write down the intensity for the polychromatic light source. We are plugging now the value of equation number 16 in that expression. So look at the intensity expression. This is the intensity at the image plane as a function of u and v is equal, will involve double integrations, and you know that this is what we have already explained. Notice that kappa in the two expressions, in the two integrals, that is kappa of u minus zeta 1 and v minus eta 1, and the other kappa which is a complex conjugate of kappa as a function of u minus zeta 2 and v minus eta 2, these two kappas are independent of time. And you know that when we writing down the polychromatic case, we also wrote down them as independent of time, and there we explained why we are writing them. That is why we were writing the amplitude transfer function or amplitude point spread function independent of time for the even for the narrow band polychromatic light source. And you know that here in the polychromatic source, this Jg, which is a function of zeta 1 and eta 1 and zeta 2 and eta 2, but you know that implicitly it also depends upon time, as we have described in equation over here. So this was the equation number in 13, in which it was time dependent, and you know that time is explicitly is available. But you know that on the left hand side we have no time dependence, because it implies that the right hand side quantities has time dependence. But you know that for the case of coherent source, as given as in equation number 16, we shall see that there is no time dependence on the quantities on the right hand side. So this is the expression that we have borrowed for the case of narrow band polychromatic light source. But you know that in the second expression we have replaced the Jj by the quantities taken from equation number 16, that is for the case of coherent imaging system. So the second expression, this one for the intensity at the image plane, is for the coherent case, in which there is no time dependence on the quantities Ug and Ug, the complex conjugate of Ug. These two quantities do not involve time. So you see that now we can write down these quantities separately with their associated integrals. For example, with the first integral we can write Ug as a function of zeta 1 and eta 2, and for the second case we can write, for the second integral we can write this as a complex conjugate of Ug as a function of zeta 2 and eta 2. Now the two integrals are quite independent of each other, and we can write these two integrals for the case of coherent case, which we have already discussed. So you know that these two quantities are the coherent quantities, because these integrals do not involve time. So it means that they are written for the perfect coherent case. So let's write the corresponding intensities represented by these integrals over here as in equation number 17a. So for the first integral we have written the amplitude, complex amplitude Ui as u1, v1, and the second integral corresponds to the field Ui, the complex conjugate of image intensity at the point u2 and v2. So this is the product of two fields at the 2 points, at the two neighboring points. One is u1 and v1, the other point is u2 and v2. And on the left hand side we have the intensity, that is I at the image plane at the coordinates u and v. So when the 2 points coincide, and then the coherent case is applicable where the intensity is given by. So you see that if these 2 points, that is u1 v1 and u2 and v2 coincide, that is overlap with each other, then you know that we can write down the expression for equation number as given in equation number 17b. That is the amplitude will be taken as the absolute square of the amplitude, and it also is equal to the absolute square of the integral. And you know that if this integral is written, we have already written this integral previously in some of the slides for the perfect coherent case, and you know that this is what we have written again in equation number 17b. So it means that starting with the polychromatic source, using narrow band polychromatic light source, assuming that it is the case of coherent case, referencing the object points with respect to the field, the phases of the object points with respect to the phase of the origin, and also using the normalization constants, so that we can ensure that we are writing down in exact intensity expression. And then you know that the time averaging was vanished out, as in case of the mutual intensity we wrote down for the equation number 16, no time dependence is there. And then you know that in the polychromatic case, as the first integral shows, where Jg is taken from this expression, that is Jg is time dependent. On the right hand side you can see that time is there. So you see that starting with the polychromatic intensity expression, and then plug in the equation number 16 there, and then separating out these two integrals, and then of course writing down the corresponding amplitudes there, and then assuming that these 2 points are close to each other, that they coincide with each other, we have written down the intensity for the case of the perfect monochrome, for the perfect coherent case, as given in equation number 17b. So equation number 17 is for a coherent imaging system. A coherent imaging system is linear in amplitude. The convolution of amplitude PSF, which is kappa over here, with the amplitude geometric optics image, which is UG of zeta and eta in equation number 17b, means that equation 17 is applicable to the invariant system also. You know that you can recognize the integral in equation number 17b as the convolution between kappa and UG. And you know that when we can write some integral in the form of convolution, it means that the system is invariant. And so this 17b represents a coherent imaging system, and in principle an invariant coherent imaging system. So this also shows that a coherent system is highly nonlinear in intensity. So the coherent system is linear amplitudes and highly nonlinear intensities, because the intensities involved the absolute square of that quantity. So due to being absolute square, it is highly nonlinear in intensity. But you know that if you look within the integral, you have, if you consider the within the integral, all the quantities are in the amplitude form, and you know that these amplitudes have only unit power, and that is why the coherent system is highly linear in amplitude. And when you talk about the intensity, that is the absolute square of that integral, it means that the integral in intensity represents that the system is highly nonlinear in intensity. The analysis was started with a narrow band polychromatic light source, which under certain conditions converted to the case of a perfect monochromatic case, as we have presented in figure in equation number 17b and also listed in equation number 5. Assumptions used in deriving equation or in arriving at equation number 17b are: number 1, the main contribution to the amplitude impulse response comes from the central frequency nu dash or nu prime, and not from the frequencies around that. So you see that if we are using a narrowband polychromatic source, there is a central frequency which we have represented as nu inverted hat. This quantity, the frequency, that is the value at this frequency, is highly dominant in comparison with the frequencies in the neighborhood of this central frequency. So we are assuming while writing the amplitude impulse response, that is while writing the kappa expression, we assumed that the main contribution to the kappa is coming from the central frequency and not from the other frequencies. This is what we have also assumed when we were writing the expression for a narrow band polychromatic light source. As you can see that this intensity expression that we have written, the first intensity expression, also involves kappa, and you know that this kappa does not involve any time dependence. So it means that this kappa was written only for the central frequency. So for the polychromatic source, we can also write kappa for independent of time, and this is also what we have assumed for the case of coherent imaging system, narrow band coherent imaging system. So this is the first case that we have written kappa under the condition number 1. The second is that the phases at all image points or at the all object points. So if we talk about the object points, you will say that the phases at all the object points at the object plane are referenced with respect to the phases at the origin. And similarly, you can also give the same statement for the image points. So in equation number 2, we have given the same statement for the image points, that is the phases at all image points on an image plane thus change with the change of phase at the origin, a phase reference point. So the origin, so the points, so the center of the origin, that is we also referencing the all the points on the origin also with respect to the phase at the reference point of the origin, or at the phase value at the origin. And the number 3 point was that when the two neighboring points on the image plane coincide. So you see that here we are assuming that u1 and v1 and u2 and v2 coincide with each other, and under that condition we have written the expression given in equation number 17b. So you see that this is the effort that we have done in this case, that we have converted our coherent case, that is the coherent imaging case, from started with narrow band polychromatic light source, and then assuming these assumptions that we have also given, and assuming that the all the points at the object plane will be referenced with respect to the phase at the origin. And similarly, on the image side, we can also say that all the image points, that is the phases of all the image points, will also be referenced with respect to the center of the image point, that is the origin of the image points, which we have also referenced, which we have also called the referenced point. So you see that using these assumptions and assuming some constants, some normalization constants that we have introduced in equation number 14 and 15, so that we can give an exact expression for the intensities. We have written down the expression that over mutual intensity in case as given in equation number 16 is independent of time for the case of coherent case. So you see that using these one we have obtained the intensity expression, and also assuming that the 2 points at the image plane coincide with each other. Under that condition we have written equation number 17b, and you see that this is what we have also written down such an expression for the perfect coherent case. And you know that kappa is already we have made it independent of time even when we were using a narrow band polychromatic light source. And you know that here we can say while looking at this expression, that is looking at the unity power of ug and kappa within the integral, that over amplitudes, over a coherent system is highly linear in amplitudes, and looking at the absolute square of the intensity, we can say due to being absolute square over intensities are highly non-linear even for the case of coherent imaging system. So this is what we have explained, all what we wanted to explain. So this is the end of slide number 57.